It's a pleasure to have today on Wang, currently at NYU, but a very well-known face in Princeton. And she's going to talk about restriction estimates using decoupling theorem and incidence of views.
Thank you very much for the invitation. It's a great pleasure to be back at the IS, speaking the analysis seminar. I'm going to talk about restriction estimates using decoupling and incidence geometry. This is joint work with Shukun Wu. Let me first, because this is an analysis seminar, so I will try to talk about restriction first. Suppose the f is a function supported unit disk or unit ball in Rn-1, and we define the extension operator. The extension is the dual of restriction as EFX. X is a point in Rn. The EF is now a function in Rn defined as so what it means is that the Fourier transform of EF in Rn is supported on the truncated paraboloid. And the question in restriction theory that people study is what's the LP norm of EF? And we give an equivalent. This is heavy. In the restriction conjecture, Stein's restriction conjecture says the following. For any p greater than 2n over n minus 1, there exists a function only depending on p such that the LP norm of EF in Rn is bounded by was also the dimension, and the LP norm is Fourier transform. Well, this conjecture is solved in R2 and still open in R3 and higher dimensions. This conjecture is closely related to the Kakeya conjecture. Yeah.
Recording in progress.
Sorry. Okay. Better if I put the Kakeya conjecture here, because if I move, then this will move. So Kakeya conjecture is the conjecture that appears in more than 100 years ago, and it says that any Kakeya set in Rn, so meaning that any set containing a unit line segment in every direction. Has Hausdorff dimension n. So this true conjecture is known that very closely related, like via a standard argument. The restriction estimate, restriction conjecture implies the Kakeya conjecture. In particular, if we know the restriction estimate for any p that's greater than 2n over n minus 1, then we will know that the Hausdorff dimension of the Kakeya set is greater than some number that's related to the p we can show. And this 2n over n minus 1 corresponds to n. This number comes from the example that f equals to 1 of the unit distance. But the other direction is unknown. So it's not known if the Kakeya conjecture implies a restriction conjecture. What we are going to talk about today is again a purely geometric conjecture says we call it 2n Furstenberg conjecture. That's my collaborator and I should we asked last year. And this conjecture, if true, would imply both the restriction conjecture and the Kakeya conjecture. So we proved it in R2 and we made some partial progress in R3 that gives the best known restriction estimate. So this direction uses decoupling, uses Bourgain-Demeter decoupling. So before introducing the statement of the 2n Furstenberg conjecture, we'll first discuss how these two conjectures are related via the wave packet decomposition. Are there any questions so far? So in a large ball of radius r, the reason is that instead of estimating the LP norm on the whole space, we can ask what is the LP norm in the large ball and let the radius r goes to infinity. So in a large ball radius r, we can decompose EF some over some wave packet EFT, where T is a set distinct R1 of two. So this distinct means that each pair of them, the intersection is relatively small, and that its EF satisfies its absolute value is approximately constant.
So you're not separating Fourier space, you're doing physical space.
It's both in Fourier space and physical space. I want to first state what the decomposition is and then explain a little bit how this comes from, where this comes from.
Okay, but T is sort of the composition in physical space.
Okay, let me explain where it comes from. So we know that the Fourier transform of EF is supported on the truncated paraboloid. And then we cut this, decompose this paraboloid into R to the minus half. So this little disk. And this R to the minus half is related to this R. And so here we call them theta, for example. Then we can decompose F. Theta by partition of unity. So this is the support of the Fourier transform of EF, and then the support of F is here. So we have if we have a cap theta here, then the corresponding support of EF theta will be here. And so this is like the Fourier space. And once we have decomposed that, so EF equals to EF theta. This is partition of unity. And then each EF theta now is supported on a single little cap. And this one we can decompose it now in the physical space, sum over EF in T theta. So T theta is a set of parallel tubes pointing in the normal vector of theta. So this. So for example, this cap will correspond to some parallel tubes. And then let's say this cap will correspond to some parallel tubes in the pointing in the normal direction. So that's where the wave packet decomposition come from, and with sum over all the theta, this will give us the decomposition of EF. Okay. So we're not going to use where this come from in the rate of the talk, but it's helpful to notice how the tubes are related to the function. So here we said that the absolute value of a single wave, so this is called a wave packet. EFT is a wave packet. The absolute value of a single wave packet is very simple. It's like the characters, a weight, some constant times the characteristic function of T. But if we take off the absolute value, it has some oscillation on it. So to understand EF, we need to do two things. One is how tubes in T overlap. Because if they are all disjoint, then at each point we have one loop passing through it, and each wave packet is easy to understand. So the function is not complicated. But if it overlaps a lot, then it can get EF could be large. So this step is done via instance geometry. This part, what I mean is something like this. The second is when they intersect, for example, at the common point, how the oscillation. So we'll first talk about what oscillation means here. What I mean is, for example, this oscillation, the tricky part is that EFX, so given a point, could be as large as the sum over. First of all, only the tubes containing X, the corresponding wave packet matters, because we said that the absolute value is like an constant times indicator function, so we only count the tubes passing through X. So it could be as large as this sum over, but it cannot happen for like many X. Or not so large portion of X. So this is what oscillation means. There is this L2 orthogonalities. So one example of that is say that we have a Wolff radius at 1/2. This is less than so in reality, it's like some decays. There will be some tail, but for the lecture, we just pretend that it is Wolff radius at 1/2. So this part is done via Procher inequality, so that's like that's not too hard to show, and but this is not strong enough to explore oscillation in. So the next thing that's much stronger is the Bourgain-Demeter.
What are you summing over? Which tubes are you summing over?
So all the tubes that intersect this ball.
Regardless of the direction.
Sorry, regardless of direction, yeah. If it doesn't intersect, then this means that it has negligible contribution to the radius r to the 1/2. And so the Bourgain-Demeter decoupling is like replacing this 2 by some larger p. And also replace the ball by some sets. So this is like intuitively we sort of see that we need to understand how tubes intersect to understand EF. But the Bourgain-Demeter decoupling is like a way to quantitatively show that how we can use the incidence estimate to get a meaningful bound on the LP number EF. So the one we're going to see is called refined decoupling. It's based on the Bourgain-Demeter decoupling, and it appeared in a joint work with and also this was independently discussed by Duet. It says that let X be a union of R to the 1/2 Q. We might use Q to denote R to the 1/2 balls, and EF equals to sum over this comes from the word packet decomposition, and then suppose for any R to the 1/2 ball Q containing X, the number of T intersecting Q is less than some number capital M, then we have the following. The L then for any Q between 2 and 2 n plus 1 over n minus 1. For those who study PD, this 2 n plus 1 over n minus 1 is the exponent for the streetcast estimate. They are closely related. The LQ norm of EF on this union of R to the 1/2 ball is less than M divided by the number of tubes, 1/2 minus 1 over Q. So this is the refined decoupling as theorem. It's what's interesting is that so the left hand side is X, like the union of R to the 1/2 balls, and M is the number of tubes through each ball, and T is the total number of tubes. So the relation between the three quantities X, M, and T is an incidence estimate. So that's how incidence estimate comes naturally via refined decoupling theorem to bound to the restriction. And after that, we are done with the analysis. We'll focus on talking about what kind of incidence problem we can have and what type of bound, what kind of incidence estimate we prove. Are there any questions?
Is there an easy way to understand why this 2n over n minus 1 relates to 2n plus 1 over n minus 1? What's the connection between the various Q's?
Yes. So this number is the Stein's, sorry, is the streetcast estimate. It's also called a Thomas-Stein. For example, if we put P here and Q here, so like if I simplify a little the restriction conjecture, usually there is a P and Q, if we put Q to be 2, then the best number here is the 2n plus 1 over n minus 1. Okay. Now, if there are no more questions, and if the previous wave packets are complicated, now we can forget about it and just focus on instance problem. So let's start from the beginning. And so delta is a small scale. We should think delta as r to the minus a half. If we want to relate this delta to those tubes, and then consider T is a set of delta tubes. So that has radius equals to delta and length equal to 1. So this is the rescaling of those tubes. We make the length to be 1 and the radius become r to the minus a half. With 1 point in each separated direction. So this, we call it the Kakeya assumption. As you can see that this is the discretized delta discretized version of the Kakeya set. So delta discretized. So first of all, this Kakeya assumption implies that the number of delta tubes is greater than delta to the minus or approximately delta to the minus and minus 1. And we can reformulate the Kakeya conjecture. The union of those tubes has volume. So this means that greater than some subpolynomial power times 1 of delta times 1. So it's approximately greater than 1. And as we can see in the application, usually X is a union of both, and then it's not clear that the entire tube can be containing X. So there we can deduce some quantities, say like for any T and T, the shading is Y T is a subset of T, the union delta both. So an incidence problem that can be immediately plug in this decoupling theorem is the following. So the question is, so can we give a lower bound of the volume of the union of shading? So for example, here, this X is like the union of YT after rescaling, right? So, and then the relation is so number of balls in Q and X times, so each times N is greater than is related to like sum over YT. But this problem, if we don't add any assumption on YT, then this problem is not very well posed. The reason is that so enemy example. I think I wrote this enemy example a few years ago on the same blackboard. But let me do it again. So the enemy example is that suppose we have that it exists above radius small r. Let's say r is less than 1 and greater or equal than delta, such that YT is containing BR intercept for any. So this means that we have a small ball that contains all the shading. And in particular, this means that a lot of tubes, if we only consider their shading, they clustered into the same set. So this is a very bad example.
How is the shading defined exactly?
It's like any subset of T that is a union of delta balls.
Every T has its own YT and there's no need for compatibility or something.
Sorry?
Every T has their own YT and there's no need for compatibility or anything.
Yeah, every T has its own YT. Yeah. And for now, we don't have any restriction on YT, but later we will need to add some restriction. And from this example, I will do a simple calculation to show why we need to add a list assumption on T. So for now, there is no assumption. YT is a unit of
So
delta
it could
ball.
also be just one delta ball.
Yeah, exactly. Let's look at the one delta ball example. Okay, maybe one is bad. Let's look at two delta ball example. So, yes, like suppose say each YT contains two delta balls. And let's study this simple case. There are two possibilities. One is like in the enemy example, we can pick a ball of radius 2 delta that contains all the YT. So this is pretty bad because then this means that in this is approximately delta squared or delta squared. So and then if we add assumption, let's see a baby case of what is called a 2 ends assumption. Let's say we force the delta ball on each YT to have distance about one, or like at least one half. So that's the meaning of two ends. Once we add this assumption, then it's by a Cauchy-Schwarz example, Cauchy-Schwarz estimate. We know that this is greater than number of tubes to the 1/2 times delta squared. So suddenly we gain this extra factor by just saying that they cannot concentrate, they have to be spread out. So the reason is that because they have distance about 1, approximately 1, then any, let's say greater than 1/10, then is like the number of tubes through each pair of balls is like constant. So in order to determine this many tubes, then yeah, so we know that the number of tubes is less than the number of delta balls squared. And so this means that the number of delta balls should be at least the number of tubes to the 1/2, and then we just type it. So that's a very easy calculation to tell us that why this assumption is nice. And usually if we can identify the left-hand side, we can apply some other induction argument to take care of the analysis. And this was introduced by Tom Wolff and also in the paper of Tom.
What do you get the square?
So we can pick any pair of delta balls with distance 1, or any pair of delta balls, and each tube is like these 2 delta balls, almost right.
Okay, so don't you know your tubes again? Tubes that they go in different direction, right? So
In this problem, we don't really need to know they go into different directions. So in this simple calculation, all we know is that each tube,
Tube is different.
there are the 2 delta balls that's far apart.
Counting the tubes is like counting the pairs of bolts.
Yeah.
Right,
Good.
and yes, that's why it's good.
Yes.
that's the worst case.
Yeah.
Yeah, of course.
Okay, so now we are ready to introduce the 2 ends. So the actual 2 ends assumption. This means that there exists epsilon greater than 0. Greater than 0 and this is all shaded. There exists such that for any R between delta and 1, and any BR, the shading it cannot be concentrated on a ball of radius. It cannot be concentrated on any small ball, and this epsilon measures how much it's not concentrated. in particular, this is a number that's much smaller than one. When R is less than one. So that is the two ends assumption. And the conjecture is so the two ends Furstenberg conjecture is suppose T is a set of delta tubes satisfying the Kakeya assumption. And well, each T in T a shading, we have a shading y T satisfying the two ends assumption.
What defines exists a shading satisfying the two end?
Yeah. Like any shading that is right.
Any shading.
Usually this epsilon is fixed at the beginning, and then the volume is greater than is greater than and let's say and yp is greater than lambda times the volume t, and this is greater than lambda times to the n minus 1 over 2. So that's the conjecture, and this conjecture, for example, if we take lambda to be approximately 1, then this conjecture implies the Kakeya conjecture. So maybe let me see. Let's talk about where the word Furstenberg come from. So because originally there is
So this inequality has to be satisfied for any T satisfying the Kakeya assumption and for any shading
yes.
with the two ends assumption to satisfy that inequality.
Yeah.
That's
In the Kakeya problem, there's a difference between Hausdorff dimension and Minkowski dimension. I think that. Since we're talking about Minkowski version of Kakeya
No,
conjecture.
this is all about Hausdorff version. Yeah. So if you allow lambda to be like say delta to the epsilon or another epsilon or even 1 over some log delta, then if you know that, it will imply the Hausdorff dimension. Also, let me say here that this so-called Kakeya assumption is not very essential. So this is just a simpler way of introducing the problem. In reality, this should hold for set of tubes satisfying the same dimension as. Okay. It's okay. This is more complicated, so maybe I'll move it to the end. But I want to say that this is not a very strict assumption. Um. So the original Furstenberg set conjecture. We need to take. So in the epsilon in the 2s assumption, we need to take epsilon to be log lambda delta minus. So this is stronger than the Furstenberg conjecture because we are happy with any epsilon greater than 0, but in the Furstenberg set conjecture, it tells you what this epsilon has to be. But our proof is based on what we know about Furstenberg conjecture in R2. So when n equals to 2, this was proved by Kevin Ren and myself. And then following a sequence of work by opponent Schmerkin. So in fact, opponent Schmerkin did a large part of the problem. They use mostly tools from geometric measure theory, and Kevin and I we use some Fourier analysis to finish the other half. So let me say the theorem. Is that this conjecture is true in R2, and this we use the Furstenberg estimates that we proved in R2 as a black box. So following Furstenberg estimate. And also this a large part of the argument already appeared in the and slightly earlier work of this Decoupling-Demeter. But in this paper, we didn't think of using incidence estimate to work on restriction problem. And we also have some partial progress in R3. We proved that this is greater than lambda to the three-quarters. So we use the result in R2 as a black box combined with some an earlier argument of Tom Wolff to prove this theorem. So in terms of application to restriction in three restriction estimate holds for any e greater than. So this is this number is meaningful because it implies via the standard restriction imply Kakeya estimate. It implies Wolff's hairbrush. But like the Hausdorff dimension of a Kakeya set has dimension greater or equal than 5 times. And this means that we cannot. So if we want to have any quantitative improvement of this restriction estimate, we would have quantitative improvement on the Kakeya bound, which is very difficult. People have been trying to do it for many years. So that's lava and top. They show that the Minkowski dimension so exists epsilon greater than 0, the Minkowski dimension is greater than epsilon. Also, in terms of the restriction estimate, the previous work is both using a polynomial method, so p greater than. In my thesis and also with Shukun, we like further refine the polynomial method to get some other improvement. But for this result, we didn't use polynomial method. We use, as you see, decoupling and incidence geometry.
So what is 3 plus 1/4?
The restriction estimate in R3 goes for p greater than 3 plus, or any p greater than 3 plus 1/4. But the conjecture is 3. And we make the range a bit larger. I guess I'll stop here. Thank you.
Questions?
So, how easy is the implication that Stein restriction conjecture implies Kakeya?
Yeah, this is so we can take for any Kakeya set, we have a set of tubes, right? And then we can just construct EFT to be about a heuristic function of tubes. And then there is the Kinshasa inequality. So we can take so each T is associated with unique theta. And the expectation of epsilon theta. I won't tell you which epsilon theta, what this means. So epsilon theta equals to plus minus 1 with half probability IID. And this is about the same as sum over the F. So because each T corresponds to a unique theta, so this is, and the right-hand side. So because the restriction estimate tells you that this is less than something, and so you have this is less than something. And then the left-hand side is basically if you translate back to using so each absolute value of ET is like indicator function of T, then this is essentially an incidence bound.
Are you able to say anything in higher dimension?
Oh, yeah, yes. So we also obtain improvements in higher dimension, but the bounds are not are not like this one that has a meaning.
You mean it's not computable or?
Oh yeah, it's sorry, it's computable.
It's computable.
So it's explicit numbers, but Yeah, the numbers are improvement, but they don't have like a geometric meaning.
Oh, they don't have a geometric meaning in
Like
terms of the
this,
Kakeya.
yeah, like this is the threshold that we cannot really do
Mhm.
anything. So that's why I focus on 3D and 2 dimensions.
Well, you don't need to go through restriction estimates to deduce Wolff's bound from your theorem, right? Your theorem immediately implies that the Hausdorff
Yeah,
dimension
this immediately, yes, this
implies
is
the Hausdorff
true,
dimension is
a more
5
refined
halves.
version, yes. But all I want to say is that this shows for in terms of restriction, one cannot really improve explicitly. In other words, previously, we were not sure that if decoupling handles oscillation for the restriction problem, but for now, we think that at least for the restriction conjecture, oscillation can be handled by decoupling.
Okay, if there are no more questions, let's thank Hong again.